Hi, welcome back. We're starting a new chapter on alternate current. So, what is this alternate current? So, till now we have actually studied trying to understand what is electromagnetic induction, and we also studied how magneticity and electricity are, in some sense, related. All that. Now, we know that we can actually generate electricity using magnetism. So, using Faraday's law of electromagnetic induction. And we also know that how to construct a generator which gives out a alternate current or an alternate varying voltage or current. So in that we figured out that the uh, generally when the current or voltage which we're talking about from the AC generator comes out not like simply randomly varying, it varies quite smoothly. Okay, and we also found out that that variation is almost similar to what we call a sine wave, like this. That means if you actually look at how the voltage or current varies, okay, it varies in the same way as a sinusoidal function. So what is the meaning of that? What is the meaning of sinusoidal function? So that means that if you actually take, for example, this if you take sine values like sine 0, sine 30, sine 40, 45, sine 9, sine 90, like that, if you plot all those values, they look like this. Okay, and if it happens to be the angle, because these are all the angles that you can plot. So in the sense that at this point it is 90 degree, here 180 degree, 270 degree, like 360 degree, like that. In which case this would have become basically angle like theta. Okay. But if theta is varying linearly with respect to time, that means a rotating kind of a scenario, okay, then you can also call this as, if theta is varying with respect to time like omega t, it varies with respect to time, okay, like omega t, then you can call this also with respect to time. So this is how an AC voltage looks like. The reason we call it alternate current is because it is actually uh, going up and down, in the sense that it is going above 0 and below 0, means it is changing the direction. It is positive and negative, so it is changing the direction. So this is the current that we use regularly, is always at home. At home, if you see the plugs from where the current comes or the power comes, it's all alternate current. So the scientist who worked extensively on this, his name was Nicholas Tesla. He actually worked on creating industrial grade uh, alternate current generators. So we call them as alternators. They are generators, but they generate alternate current. So the supply of electricity to home, initially when Edison tried out, they were actually in terms of DC voltage. So they were not running any wire. They used to charge batteries and deliver the batteries in a truck to your home. But when Tesla argued that instead of that, you can send a alternate current through wires, and the loss through wires of alternate current when you send is very less. And there was actually a huge amount of trade war between Tesla and Edison during that time. But finally, it was finally we know that Tesla's idea has actually won on this one. So we still have alternate current at home. Okay. So what we will see now is that since we use alternate current in all places, now how do we do any kind of circuit analysis for alternate current? So what happens if an alternate current flows through a circuit? Unlike a DC current, which we always say whenever current flows 3 amps, 2 amps, something like that we used to say. Okay, it was just one value. Now it is continuously varying. So when a varying current flows in a circuit, some interesting things happen. So we're going to watch what those interesting things are and see how to analyze the circuit when there is an alternating current flows through it. So we start with resistor. Okay, resistor actually, if you see, is a uh, is not going to be greatly affected by whether you are using an alternate current or a direct current, DC. As against alternate current, we call DC, okay, direct current. So there is not much difference. So we'll just see how that, what is the meaning of that. Okay. So here we're going to put it as, let us say, uh, this is our voltage. I will call this as basically V or something like that. But in this case, V is not just one constant value. So we will say V is actually equal to some Vm into sine omega t. As the time is varying, it varies like sine omega t, like a sine wave. Okay, the maximum value of that for a sine function is actually 1. Sine 90 is 1. So since sine function is 1, so maximum value of this is Vm. So it cannot exceed Vm. That's why I call V max. Okay. So if you draw it, actually it looks exactly like what I showed you. Only difference is that this point is V max and this is T. So we're going to have our Vm like this. Now if we put this here, now what the current actually flows, let us say like this. So we are going to put the current like this. Okay, it doesn't mean that current is always going to be like this. Okay, it is just our convention. So it goes like this and back like this. It keeps varying. Okay, it's a varying current, but we will say that current flows like this. So when we say that, we can apply actually Kirchhoff's voltage law readily here. So we can say voltage. What does the voltage law say? V minus, so we will write V of t because it is a function of t. Okay, we can say this V is actually a V of t. We will generally use lowercase letters for variables and uppercase letters for constants. Okay, unless specified otherwise. So in this case, this is actually a constant Vm. So V of t is minus, if you go this way, and let's say the current is I. So I'm going to call current again small I. It means a variable. It keeps changing. So minus I into I of t, okay, into R is equal to 0. This is our straightforward Kirchhoff's voltage law. Okay. So this is the current, the voltage, and this when you are going from in this direction, same as the loop current, you will take it as minus and do it. So if we write it as, in this case, if you want to write it as I of t, then will become, if you see, okay, V of t by R. Or we can say V of t can be substituted with this, is equal to Vm sin omega t by R. Like that we can write. So we can also write it as Vm by R, okay, Vm by R into sin omega t. If you if you look at it, basically this is a constant. We can call this constant Vm by R as Im, okay, I max sin omega t. So this is our I. So our I is Im sin omega t and V is Vm sin omega t, and Im is nothing but Vm by R. Okay, so there is nothing great that we have discovered here. Okay, so we already know this is basic Ohm's law. So if you want to plot that Im sin omega t, let's say I want to plot I also on the same graph. One can plot it as, let us say, some value of I. Something like this. What it means is that the value of the I is also varying with the same periodicity, and when this is 0, this is also 0. So that's what we're telling. Okay, only thing is its peak, whatever we call the peak of this, is nothing but Im, which is Vm by R. So we will say that these two waves, that is voltage and current, they are in sync. We say that they are in sync, means they are not actually uh, out of phase or anywhere. They are in phase. The phase difference between them is actually zero. That means, what is the meaning of that? When this is zero, the other one also zero. When this peaks up, the other one also peaks. When it becomes zero, when it becomes negative, this also becomes exactly the peak negative. So like that, they follow each other. It's called in phase. The phase difference is zero. So that is, so now we know that whenever we talk about a resistor, a normal resistor, if V is equal to Vm by Vm sin omega t, I will become Im sin omega t, where Im is equal to Vm by R. So this we have figured out now with this straightforward normal Kirchhoff's voltage law. So let's also look at basically what is the power consumed by this. What is the power consumed? So power, we always talk about I square R. Okay. Power, I'll say power is equal to generally I square into R. In this case, I is nothing but Im sin omega t. Okay, so we will write it as Im sin omega t whole square into R. So this can be written as Im square into R into sine square omega t. Now if you see, this is basically instantaneous power, which means that power basically is uh, changing, also not just current and voltage. Power is changing as sine square omega t. Okay, you can see that very clearly. Power is changing. Okay, now that power, uh, one thing we can see very clearly here is that this power is not negative any time. Power always is positive. Okay, in the sense that whether it is voltage is positive or negative, in any case, this is always positive because this is a square term, and square term is always positive. Okay, so that is the value of the power. So if we want to calculate actually the average power now over a cycle, I want to calculate the average power over a cycle. Okay. How do I calculate that? So average power over a cycle, I'll say it as Im square R average. Since it is a constant, there is no change in that. Okay. Now here sine square omega t, the average power I will say is equal to average of sine square omega t. So average of sine square omega t is basically you draw the sine square curve, or then you integrate it over a given time. Okay, and divided by the time you average. Yeah. So if you know the integration very well, it is very easy to do. So I'm going to basically not do that at this point. If you have any doubt in the live sessions, we will do it. But this average actually comes down to, if you calculate, comes down to half. This comes down to half. This whole average. Whereas sin omega t, if you take the average, like sin omega t, if you take the average over this whole period, it will become zero, because as much positive, there is also that much negative. Sin square omega t on the other hand will actually will never be zero, because it looks somewhat like this. It's double the it's always on the positive side, so it's not going to be zero, so it will turn out to be half. So if that is half, then we can say that this is nothing but Im square into R by 2. This is the average power. Now we know that in the case of DC current, power was I square R. Okay. Let's say I take two circuits. Okay. in one circuit, it's exactly similar circuits, two circuits. In one circuit, I will pass a DC current of, let us say, capital I, this much DC current. In the other circuit, I will pass this one, Im sin omega t. Okay, and I will tune the value of this I such that the power dissipation in both the resistors are exactly same. That means they both get heated up equally. Okay, in both the resistance is same. So in which case, actually, if you equate the power, okay, then we will say I square R is actually equal to IMS square R by 2. Or we will say I is equal to Im by root 2. That means if you pass a certain current, which is actually equal to Im by root 2. Okay. So Im means some value, whatever value you take for the peak of this. Im by root 2, that much of voltage, that much of current, if you pass through a resistor, okay, then the power dissipation, then you get the way amount gets heated up, same exactly as when you do a full wave that is passed through that. So what does that mean? That means that this current I is a equivalent current, okay, that heats up equally to that of a AC current. Okay, so equivalent DC current. So we call this current as RMS current. RMS. We read it like RMS. So we write it as IRMS is equal to Im by root 2. So you may ask, what is this RMS? Okay. So RMS is nothing but, we call it as root mean square. So if generally it is not only meant for a single AC current, it's in any amount of current if you take finally varying currents. If you if the value of the varying current, okay, if you take one by one and you actually take square of them and then take an average and then take the square root, that is when you will actually get this. In this case, it is a much more straightforward thing. Average is actually Im by 2, and we take the square root of that. Yeah, Im by root 2. So this is basically what we call an RMS current. RMS current is simply a way of telling how much is on an we can't say average. You know, we wanted to say actually if the current may be varying, but on the average this much current is flowing. I want to say that. Okay. Because we can't keep on saying that how it is varying, how fast it is varying, all the information is fine. But I just want to know how much on an average, how much current is going. But unfortunately, the average, if you take on the current, you get 0 because it is same equal on both on positive or negative. But we know very well that the current, what is happening to the current? Current actually is getting used up to light up, to run the fan and all that. It is getting used up. So when it is getting used up, it is actually converted also into heat. So if we can somehow say on an average how much current is flowing, so that now we measure in terms of heat, okay, in the sense that in terms of power, the current that gives same amount of power as another DC current. So that much is what we call an average. So that is why we don't look at average of the current, but average we look at basically RMS of the current. How much of the current is needed to heat up the same amount of the AC. So like, okay, so this is the average, not the average, but it is called the RMS value of current, and we are going to be using a lot about that. Whenever we talk about an AC current, we say how much RMS current. And that means that will give us an idea about how much current is flowing. Okay. Now that is the now the power, when you do like that, you substitute that here. Okay. Then power simply, average power simply becomes IRMS square into R. Okay, Im by root 2 square into R. So this is similar to with the way we work with the DC. I square R is the power. So here also it is I square R. It's just that it is the RMS value of current. So similarly, if you take, for example, in the case of voltage, if you say V voltage, V RMS is equal to Vm by root 2. If we do that, okay, then power we can actually look at now as power average power, we can say, is equal to, okay, we can say Vm by root 2 into Im by root 2 or Vm Im by 2. This is same as saying that power average power for us is simply equal to, this is nothing but Vrms and this is nothing but IRMS. Power is equal to Vi, works here also. So you can see that very clearly that whenever I'm talking about average power is equal to Im square by R, you can see that Im square by 2 into R. This is the power, correct? So you can say that Im is nothing but, we know that Im is nothing but Vm by R. We can write it as Vm by R. So we will take one of the Ims as Vm by R, okay, and another Im we will keep it as it is, and we'll keep the two as root 2 and root 2 separate, and this R we keep it as it is. So you see what I did. I just wanted to show you that this is same as this. Okay. So how am I showing that? I'm taking the Im square by 2 and split it into Im into Im. One of the Ims I keep as it is. Okay, other Im I'm going to write Vm by R. Okay, now 2 I split into two of them, root 2 and root 2. Now you see R gets cancelled. So Im by root 2 and Vm by root 2. You can see Im by root 2 and Vm by root 2, that is same as this, which is Vrms into IRMS. So what we are saying simply is that whenever you are using AC also, when you're using a resistor, it is very straightforward. Like how you multiplied currents and voltages to get power, here also you multiply current and voltage to get power. It is just that to get the, you just use the RMS values to get the average power. Okay. So whenever I talk about power, I say I use the word average, you see. But whenever I talk about current and voltage, I use the word RMS. Okay. So now I think you understood what happens. See, this is just a lot of basic math. Okay. So, but what we are, the insight is very straightforward. Insight is nothing but if V is equal to Vm into sin omega t, I is equal to Im into sin omega t. Okay, they are both sin omega t's with no phase difference between them, and Im is Vm by R. And whenever you, so one of them is like this, means the other one is like this. And one thing that we realized also is that power is, we have defined what is meant by an RMS. Okay, and we talked about power. Okay, using the power we defined the RMS. So that's all we did in this part. Okay, so now we are going to look at one more very interesting thing in the alternate currents, a new way of looking at things. Okay. So let's look at, we did already AC voltage applied to resistor. So we'll look at basically with one simple question first. Okay, we'll see one question whether we can solve with whatever we have learned. Okay, A light bulb is rated at 100 watt for a 220 volt supply. So now we are talking about 100 watt and 220 volt supply. Okay, 100 watt is the power. Power is equal to 100 watt. And 220 volt supply, what is the meaning of that? So that is the AC supply. Remember, it is AC supply 220 volts. Okay, and then we want to calculate the resistance of the bulb, the peak voltage of the source, and the RMS current through the bulb. So our question is, what is this 220 volts? Whenever they specify 220 volts, what is this? So if we know that, then we can calculate I, and we can also calculate the value of R and all these things. Okay. So if it is DC, it is very straightforward for you to do. Okay. Now if it is basically AC, what do we do? We take this, whatever they have specified to us as RMS, VRMS, or we simply call capital V, okay, which is 20 volts. So now we know the what is the maximum value. Okay, so we can calculate, for example, the peak voltage of the source. How do we calculate peak voltage of the source? We know that V RMS is equal to V peak or V max by root. That means V max is equal to 220 into root, whatever that value comes. 220 into root 2 works out to be 311 volts. You can actually just use the calculator. 311 volts. Now we want to calculate, this is the peak voltage, the resistance of the bulb. So how do we calculate the resistance of the bulb? We first of all calculate the current, okay, the RMS current through the bulb. So before going to that, okay, we know that the simple formula for us is we know power can be given in three different ways. V is into I, or we can say I square R, or we can say V square by R. In all the three ways, power can be done. Okay. Now in the DC scenario, these were just standard constant currents and voltages. But in the AC scenario, these turned out to be the RMS values. We can replace them with RMS values. So that means if we know VRMS, okay, and we know the power, then we calculate the R. So R is simply equal to, this implies R is equal to VRMS square by, sorry, P divided by VRMS square. P divided by, I take R here, P here. So VRMS square, sorry, by P, which means R is equal to, VRMS is how much? 220 square, where P is 100 watt. So this calculation you do using calculator, and it gives basically 484 ohms. So we calculated the resistor. Now RMS current through the bulb. So RMS current through the bulb, how do you calculate? So we know very well that P is equal to VI, where V and I are the RMS. So we will write it as VRMS into IRMS. So therefore IRMS is simply equal to P by VRMS, which is nothing but 100 divided by 220. That would turn out to be equal to 0.45 amps. Sorry, this is IRMS. So you can see here that whenever you're talking about alternate current, generally we have very high voltages. When you deal with small batteries, it is like 1.5 volts, 3 volts, like that. When you talk about AC current, AC voltages, generally you talk about 220 volts, 110 volts, 450 volts, 440 volts, something like that. But currents are generally small. So 100-watt bulb is a very powerful bulb. So to 100-watt bulb actually takes only 0.45 amps current. So not even 1 amp. Okay. So please understand, no, those numbers are required for you to get a feel of what it takes, what power means, how much current and how much voltage. All that you should be able to quickly think about. Okay. So if you want to have, let us say, 220 watt bulb, a 220-watt bulb in 220 volts would give you just 1 amps current. So whenever we talk about, for example, a socket of 5 amps, means to that socket you can connect actually 5 such bulbs, okay, in parallel, and it still takes it. So this is basically our uh, first problem using AC, and we used only resistor, okay, because all these bulbs are all just resistors. Okay, they are going to basically get heated up and give you light. Now we are going to basically talk about a new idea called as phasers. The new, completely new idea. Okay, so this you have probably never heard before. Right? This is called phasers. So like we know scalar, we know vectors. Okay, now we have something new thing called as phasers. So phasers are called rotating vectors, and they have a very interesting. It's just a mathematical tool to solve AC circuits very easily. Okay, so we'll just find out what they are and how to use them to solve. So first thing is, whenever you have an AC wave like this, so you can see this is an AC sine wave, you can actually say that if I draw, okay, if I take for example one circle, okay, and let us say this is my theta angle, and this height, let us say this, I am going to fully draw this here like this, okay, and let us say this height is my maximum height. Okay, let us say we call it as, if it is voltage we can say V max, Vm, and we will take actually the Vm as the radius and draw a circle. So this is Vm, radius, and draw a circle. Okay, so then if I take for example at any point in time, at any point, okay, here or here, at any point, if I draw a line like this and draw this one, okay, this height, okay, is I call actual voltage at that point. So the voltage keeps varying like this. So we call this as a V, actual voltage. Now you can see that this height is basically, I will call as V. Okay, I will call this height as V. So you can see that sine theta is equal to V by Vm, or V is equal to Vm sine theta. And if the theta actually varies, moves like this, if theta varies, then you can see that this dot traces this part. So it is like the wave. So the wave can be seen as just a Vm, if you take the radius of circle and take it around, so it basically varies exactly like that. So we can actually say, okay, that it is nothing but, the voltage is nothing but a rotating a vector. It is a kind of a vector which is rotating. So you can specify this height, okay, is v is equal to vm sin theta, and that height is nothing but this wave. Okay, and that height is the basically function of time, and that is the wave. It is vm sin theta. Now you can very clearly see that if you make it basically rotate, so it goes as with the this height, you can see it keeps moving. So we can actually say that it is a phasor. Okay. Phasor means rotating vector. So it's not a vector as such. So it's a new way of looking at it. Okay. It's called a rotating vector. So so we will say that voltage is one phasor, represented by one phasor. Similarly, current can be represented by another phasor. Okay, and those phasors need not be in phase, but both of them are going at the same pace. Remember this. If voltage is like this and current may be going in the same speed, now the rotation speed does not change in a phasor. Rotation speed is nothing but the frequency of this wave, or the time period. So that doesn't change. So only difference basically will be, in this case, one more line may be going behind this line or front of this line, depending on what is the other wave. The other wave can be another voltage wave, another current wave. So anything, we can actually represent them. And then once you do that, so we want to be able to add them, multiply them, all that. So that our aim is to make sure that whenever we had DC, it was very easy for us. We want to multiply voltage and current, we just multiplied them because they were just numbers. Here, voltage and current is varying independent of each other, and at every point you have to multiply. So how do you do that? So that gives us very good understanding of doing that using what we call a new entity called phasors. Okay, so let us just see how it even works. Okay, how to even do this. So let's say you have uh, two different waveforms. It may be two voltages or two currents, doesn't matter, two waveforms. Okay. Now, one of the waveforms you can see here, that is this blue one. Okay, here is a blue waveform. That is nothing but this arrow. This arrow is specifying us basically how this is varying. And you can see that if there is one more, for example, this one, the second one, this thing. Okay, this is specified this by this arrow. So the middle circle, and that is actually showing you here how this waveform is varying. You can very clearly see here that this waveform, okay, I will call that as basically waveform number, let us say, if this one is 1 and this one is 2. Waveform number 1 and 2 are not in phase. They have a phase difference in the sense that they are not reaching the 0 point at the same time, the blue and this, and they are not reaching the peak point at the same time. They are out of phase. How much are they out of phase? If you see, okay, so they have an angle between them. You can see here, this is the angle. That angle will be same as the, see, if you calculate here, this is coming to 0 and this is also coming to 0. Okay. So this, between these two, whatever is the time is there, in that time it traverses that much angle. So it is specified generally in terms of an angle. Okay, that they are 90-degree phase difference, 45-degree phase difference, like that. Okay, so there is a phase difference between these two, you can see, and both of them, if they are being applied somewhere in the circuit, and if you want to add those waves, then the way to add those waves is at every point you basically take this value and corresponding value here, add and draw the next one. So you keep doing that when you want to add at every point in time. You take both of them and add, and whatever the value comes, you write it as another point and then join all the points later. And it so happens that when you add these 2 points, actually you will get the other point, other one. So instead of doing all that, okay, you can actually add it straightforward here. How? I'm going to basically take this as one vector, take this as another vector, and I do a vector addition and add it to them. See, you can see that there is a phase angle for that vector addition also. Okay, that's an angle. Now, if I actually look at this particular thing, and it can generate a new circle, circle number 3, new circle, and the new circle is the addition of those two. So it is harder to do the addition here at every point, whereas doing this vector addition is simpler. So that is how, and this vector is continuously rotating. Though they are rotating, okay, we can take a snapshot and add them, because they are not rotating with respect to each other. Their angle between them is same. Okay, so they are just moving like this. You can see that they are all going in sync, but there is a difference of phase between each one of them. So you can very easily compute the addition by actually just doing the addition at the vector level. That is the beauty of the phasors. That is how you can use phasors. Okay, so I hope you got some understanding of why we use something called as phasors. Okay, so if you applied the same thing, for example, for um, a resistor, you can see a phasor diagram for the resistor. How does it look like? Okay, for a resistor, this is normal waveform. This is not the phasor diagram. Okay, this is, let us say, the voltage. This is Vm, and V is varying like this. This is our time. Okay. And let us say I'm going to draw from this point to here. So with Vm as basically the radius, I'm basically going to draw a circle with Vm as the radius. And the V is nothing but specified by this particular phasor, which is rotating. I have taken a snapshot, but it is rotating. This is V. Then so V is what now? You can say that V is nothing but Pm sin omega t. So if you take this one, for example, then let's say this is I, okay, and this is actually in kind of in phase with this. That means it is going up and down at the same points. Okay. So this, let us say, is Im, I maximum. So we can take a line which is at the height of the Im like this, and take that as a radius and draw a circle. Okay, in that circle I'll have to draw I, okay, which is basically nothing but I is equal to Im sin omega t, and you can very clearly see that this one from here to here is I, and that I is equal to Im sin omega t. Why am I drawing this vector on the top of this vector? It is because there is no angle between them. There is no phase difference between them, and hence this line and this line are just two lines, one above the other. There is no angle between them. So one of them is current, other one is voltage. So the phasor diagram, simply if you want to say, I want to draw the phasor diagram for a purely resistor circuit. It will be simply nothing but if you draw voltage like this, the current also will be on the top of it like this. That is the phasor. Just two lines, two arrows, one representing V, another representing I. In our mind, we know that it is actually rotating and creating this kind of a waveform. Okay, that is the phasor representation. So, with that understanding of a very simplistic scenario, now we'll move forward to understand how an AC voltage when applied to an inductor. Okay. Here is real AC coming into picture. Till now, AC voltage and DC behaved in the same way. Now it actually behaves differently. When you talk about an inductor, okay, what happens when you apply an AC voltage to an inductor? And how does its phasor diagram look like? That we will see in the next session. Thank you.